major finding of this project is the discovery of signs of a gas, phosphine, pH 3, in the upper atmosphere of Venus, altitudes about 55 kilometers. Phosphine is difficult to produce in Venus and difficult to survive. So if some was dumped in there magically, it would go away very quickly. So the fact that we found it there means there must be something producing it. What produces phosphine? There are a few processes that can produce it, but most of those processes known processes don't apply on Venus or won't produce anywhere near the amount of phosphine that we've found. So we are left with the conclusion, either there's a process we don't understand at work, or a process that we do know that can produce phosphine on Earth is at work, and that process is life. The kind of life that produces phosphine on Earth is bacterial. So this is at places like penguin colonies where they're acting on the guano, to use the technical term, produced by the penguins. So bacterial single-cell organisms is by far the most likely, but we have no information really on what might be going on there. But the basic assumption is it's going to be unicellular life that's functioning either photosynthetically or chemosynthetically and generating phosphine as part of its biological processes. Venus, to quote or paraphrase Carl Sagan, is hell. Its surface temperature is high enough to melt lead. Its surface atmospheric pressure is about 600 times the atmospheric pressure at sea level on Earth. A place less favourable for the existence of life than the surface of Venus can hardly be imagined. However, we're not talking about the surface of Venus. We're talking about cloud decks at altitude of about 55 kilometers. And at that height, the pressure is about equivalent to sea level atmospheric pressure on Earth, and the temperature is at about the right temperature for liquid water to be possible. Now, that's not going to be liquid water the way you'd pour it from a jug here. It's going to be in droplet form, and because Venus has an awful lot of sulfur dioxide in the atmosphere, that water is effectively going to be, well, fairly concentrated sulfuric acid. So it's still not very pleasant. But there are extremophile bacteria that can survive in very acidic environments on Earth.
So we originally found phosphine in the upper clouds of Venus using the James Clerk Maxwell telescope. And that observation, it was a weak detection. And so what that allowed us to do was actually ask for more time to observe and confirm that phosphine was in the upper cloud decks of Venus using a powerful telescope in the Atacama Desert in Chile. And so that was using the Atacama Large Millimeter Submillimeter Array, or ALMA for short. And so not only did we confirm phosphine in the upper cloud decks of Venus, we then were able to find out where the phosphine was coming from. And it seems that the phosphine in Venus's atmosphere is coming from an area in between the poles of Venus and the equator of Venus. And so far we've modeled our observation. We've not been able to explain the amount of phosphine that we're seeing using chemistry in the atmosphere, using how the sun interacts with the atmosphere. Even we've looked into producing phosphine by lightning and volcanoes. Nothing is able to produce our observation. And so it's really exciting to think that this phosphine detection might actually be evidence for life in the upper clouds of Venus. Hawaii was an integral part of possibly finding life in another place in our solar system. And I think for all of us, that means that when we look up in the night sky, it means that we might not be alone in the universe. For me personally, it was an overwhelming experience to even find phosphine in the atmosphere of Venus. None of us in our team really expected to find anything. We were just hoping to kind of test out the observation and maybe put some sort of upper constraint on how much phosphine might be in the atmosphere of Venus. So it was incredibly unexpected, incredibly overwhelming, and it's a really exciting thing. Now, we still have lots of work we need to do. So one of the things we're hoping to do is continue monitoring the amount of phosphine that's in Venus's atmosphere, but also in the future, really we need to send a spacecraft out to Venus to take a sample of Venus's atmosphere to really get an idea of where this phosphine is coming from. Now, on Venus, we think that it's been theorized for many, many years that Venus may have had life on it billions of years ago. But Venus, unfortunately, began to heat up because of greenhouse gases and the greenhouse effect. And now Venus on its surface is incredibly warm. So it's over 450 degrees Celsius or over 850 degrees Fahrenheit. But we think that if there was life on Venus, it will have kind of migrated upwards into the upper clouds, and it may be existing there instead, where it's much cooler and the pressures are much more comparable to that of the Earth. So if there is life on Venus, it's very possible that it's existing in the upper clouds, and similarly, one of its waste products would be phosphine, which is why the phosphine observation is so exciting to us.
And this other thing is, these are all mechanical switches.
Yeah.
So you have to literally do this.
I work for the East Asian Observatory, which runs the James Clerk Maxwell Telescope, and I am the deputy director of that telescope. My background actually is in building instruments, kind of like the one you see here. I'm actually an instrumentation scientist. So the instrument we have here is called RXA, and this instrument is over 30 years old. What's amazing about these instruments in the submillimeter is they work kind of like the radio in your car. And we tune them to a very, very precise frequency. When we tune to that frequency, we know exactly what molecule that must be emitted from. Just like when you tune to your favorite radio station, you know you've got the radio station that you like. The other amazing thing about this instrument is, unlike your phone, which might have 12 million pixels in it on a chip that big, this rather bulky instrument has 1 pixel. So just one tiny little pixel has potentially discovered life on another planet. It is also the instrument that helped to image the black hole Pavesi. So it is the little receiver that could. And I couldn't be more proud that this is the instrument that has been delivering us results of this magnitude here on Mauna Kea.
So my first reaction when I saw the detection of phosphine from Venus was I cried. So it was an incredibly overwhelming experience to really see a detection of this molecule in the atmosphere of a rocky planet that's so close by. And I think, many people choose to be astronomers because when they look up at the night sky, they want to know if we're alone in the universe. And so it's kind of making a step in the direction that we might not be alone in the universe.